Last episode, we cleared up 3 derivative rules and ended on a warning. The derivative of a sum is the sum of the derivatives. Clean, easy, true. The derivative of a product is not the product of the derivatives. That one is so tempting that I would estimate, conservatively, a quarter of every wrong answer on a first-year calculus exam comes from committing to that exact mistake. Today we fix it. We'll derive the product rule from the limit definition using a one-line algebraic trick. Look at the geometric picture in terms of rectangle areas that explains why the formula has the shape it does, then derive the quotient rule from the product rule. 3 worked examples to make the rule's muscle memory. A note on Leibniz publishing the product rule for the first time in 1684, and 1 sign trap in the quotient rule that costs more points on the AP exam than any other algebra error in the entire subject. By the end of this video, you'll differentiate any product or quotient of 2 functions you can write down. Quick recap of the pitfall, since the whole episode is built around fixing it. The derivative of f times g is not f prime times g prime. The clean counterexample, the one we drew last time, takes s equal to x squared and g equal to x cubed. The product is x to the 5th, and the power rule says the derivative of x to the 5th is 5x to the 4th. The wrong way, multiplying the derivatives, gives 2x times 3x squared, which is 6x cubed. 5x to the 4th and 6x cubed are not the same function. End of story. The product rule we're about to derive gives the right answer, and built into the structure of that rule, you'll see, is both an f prime g piece and an fg prime piece, joined by a plus sign. The same trap exists for quotients. The derivative of f over g is not f prime over g prime. The quotient rule patches that one too. 2 rules, both today. Here's the rule. The derivative of f times g equals f prime times g plus f times g prime. Read that twice. Each of the 2 terms on the right has exactly 1 prime. One factor gets differentiated, the other stays the same. Then you swap which one gets the prime and add. That is the entire structure. In words, you might memorize it as the derivative of the first times the second plus the first times the derivative of the second. Notice the symmetry. If you swap f and g, you get g prime f plus gf prime, which is the same thing in a different order. The product rule treats both factors equally. Now we have to prove it, which means cranking it out of the limit definition. The proof uses one algebraic trick, the add and subtract move, and the rest is bookkeeping. Set up the proof. Let big F of x denote the product f of x times g of x. By the definition of the derivative, big F prime of x is the limit, as h tends to 0, of big F at x plus h minus big F at x all over h. Substituting in, that's f at x plus h times g at x plus h minus f at x times g at x all over h. Stare at the numerator for a moment. It contains 4 function values, f and g, each evaluated at x and at x plus h, nothing factors. There's no obvious h to pull out. And critically, there is no f at x plus h minus f at x sitting anywhere, which is what we need to recognize the difference quotient for f. Same problem for g. The proof's only difficulty is manufacturing those differences out of an expression that doesn't seem to contain them. The trick is one of the slickest in the textbook. Here it is. In the numerator, add and subtract the quantity f at x plus h times g at x. You're allowed to do this because you're adding 0, but the rearrangement reshuffles the 4 function values into a useful pattern. Look at what falls out. Group the 4-term expression into 2 pairs. The first pair is f at x plus h times g at x plus h minus f at x plus h times g at x. The 2 share a common factor of f at x plus h, which you can pull out, leaving f at x plus h, multiplying the quantity g at x plus h minus g at x. The second pair is f at x plus h times g at x minus f at x times g at x. Now g at x is the common factor. Pull it out, and you're left with g at x, multiplying f at x plus h minus f at x. So the numerator, after the trick, equals f at x plus h, times the difference g at x plus h minus g at x, plus g at x, times the difference f at x plus h minus f at x. Both of those differences are exactly the kind of thing we want to divide by h. Divide the whole numerator by h. The h distributes through the plus sign, giving 2 terms. The first term is f at x plus h times the difference quotient for g. The second is g at x times the difference quotient for f. Now take the limit as h goes to 0 piece by piece. The first factor, f at x plus h, tends to f at x, because f is differentiable at x, and last episode's theorem says differentiable implies continuous, so the limit of f at x plus h is just f at x. The difference quotient for g, by the definition of the derivative, tends to g prime of x. The first term as a whole tends to f at x times g prime of x. The second term, g at x, is a constant with respect to h, so it just sits there. The difference quotient for f tends to f prime of x. Second term tends to g at x times f prime of x. By the limit law for sums, the whole limit is f times g prime plus g times f prime, which, reading the terms in the conventional order, is f prime g plus fg prime. The product rule is proved. The algebraic proof was airtight. Now the picture that explains why the formula has the shape it does. Imagine f and g as the two sides of a rectangle. The area is f times g. When x moves by a tiny amount, f grows by df equals f prime times dx, and g grows by dg equals g prime times dx. Look at the picture. The original rectangle is the blue piece in the middle. The new rectangle adds three regions: an orange strip on top, area f times dg, a green strip on the right, area g times df, and a tiny red corner square, area df times dg. Here's the punchline. The corner square is the product of two small quantities. It's second order small. In the limit as dx goes to 0, that corner vanishes faster than the two strips. What remains is f times dg plus g times dff, exactly the product rule. The add and subtract trick from the proof is the algebraic shadow of this picture. The corner is what gets added and subtracted. The two strips are what survives. A short history note. The product rule, in essentially the form we just proved, made its public debut in October 1684 in a paper Leibniz wrote for the journal Acta Eruditorum in Leipzig. The paper is called Nova Methodus pro maximis et minimis, a new method for maxima and minima, and it is the first public document in the history of calculus. 6 pages. In it, Leibniz introduced the denotation for differentials and listed the basic rules of his new calculus. The product rule, written in his original notation, was d of xy equals x dy plus y dx. Divide both sides by dx, the differential of the independent variable, and you get exactly what we just proved. The same paper gave the quotient rule, d of x over y, and the rule for d of x to the n. Newton had derived equivalent results more than a decade earlier in his private manuscript, De Methodus Serierum et Fluxionem, which he wrote in 1671 but did not publish during his lifetime. It appeared in print in 1736, 52 years after Leibniz. Because Leibniz published first and his notation won, every textbook in the world calls this Leibniz's rule. The formula has not changed since. First worked example, the kind of thing you'll do thousands of times. Differentiate x squared times sine x. The product rule is the right tool because the function is a product of two pieces that you know how to differentiate individually. Label them. Call f equal to x squared and g equal to sine x. Compute the two derivatives. F prime of x is 2x, by the power rule from last episode. G prime of x is cosine x. Now, I owe you a small IOU on that one. We haven't actually proved that the derivative of sine is cosine. We will in episode 7 by computing the limit definition from scratch with some clever trigonometry. For today, take it on faith. Now plug into the product rule. F prime g plus fg prime becomes 2x times sine x plus x squared times cosine x. That's the answer. Quick sanity check. At x equal to 0, the first term is 0 because of the 2x, and the second term is 0 because of the x squared. So the slope at the origin is 0. The function x squared times sine x near the origin is dominated by the x squared factor. It sits down against the x-axis like a flat dish. Slope 0 is exactly what you'd expect there. The product rule produces it immediately. On to the quotient rule. Theorem, the derivative of f over g equals f prime g minus fg prime, all divided by g squared. Conditions, g of x can't be 0 because you can't divide by 0, and both f and g need to be differentiable at x. In words, the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Compared to the product rule, same two terms in the numerator, but now there's a minus instead of a plus, and the order matters because of that minus. F prime g and fg prime are no longer interchangeable, and the whole thing is divided by g squared. 3 asymmetries with the product rule, and all 3 are places where students lose points. You can think of the quotient rule as the product rule with a sign trap, and we'll be careful about which term comes first. Here's the derivation, and it's a beauty. The trick, assume f over g is differentiable and call it big Q. Then f equals q times g by the very definition of q. F is now a product, and we can apply the product rule we just proved. Differentiate both sides of f equals qg. The left is f prime. The right, by the product rule, is q prime g plus qg prime. Solve for q prime. Move the qg prime term over. Q prime g equals f prime minus qg prime. Substitute back what q is, f over g, into that last term. So q prime g equals f prime minus f over g times g prime. Divide both sides by g, put both terms over the common denominator g squared, and the right-hand side becomes f prime g minus fg prime all over g squared. That's the quotient rule. 3 lines, leaning entirely on the product rule plus a slick choice of what to call a product. A direct proof from the limit definition using a similar add and subtract trick also works. I'll leave that as an exercise. Before we use the quotient rule on an example, let me give you the standard mnemonic. It rhymes, which is the point. Low d high minus high d low all over the square of what's below. Low is the denominator, what's on the bottom. High is the numerator, what's on top. D high is the derivative of the numerator. D low is the derivative of the denominator. So the formula reads, low times d high minus high times d low all over the square of what's below, meaning g squared. That gives you g times f prime minus f times g prime over g squared. Same answer as before in a different grouping. The rhyme exists because the order of terms in the numerator matters and the rhyme locks it in. If you start with high d low minus low d high, the sign comes out reversed and your tangent slopes will all be negatives of what they should be. I've graded that error so many times. Memorize the rhyme. Recite it to yourself before every quotient rule problem until it's automatic. Second worked example. Differentiate the quantity x squared plus 1 all over x minus 3. Quotient rule territory. Label the pieces. Top is f equals x squared plus 1. Bottom is g equals x minus 3. Compute derivatives. F prime is 2x, g prime is 1. Now write the quotient rule. The numerator is g times f prime minus f times g prime, which is x minus 3 times 2x minus x squared plus 1 times 1. The denominator is g squared, which is x minus 3, quantity squared. Expand the numerator carefully. First piece, x minus 3 times 2x is 2x squared minus 6x. Second piece, x squared plus 1 times 1 is just x squared plus 1. Subtract 2x squared minus 6x minus x squared minus 1. Combine like terms. 2x squared minus x squared is x squared, minus 6x squared minus 1 stays, minus 1 stays. Numerator simplifies to x squared minus 6x minus 1. Don't expand the denominator. Leaving x minus 3 squared in the denominator is cleaner and easier to evaluate at specific x values. Final answer, x squared minus 6x minus 1 over x minus 3 quantity squared. Notice how the algebra cleanup matters. The unsimplified version is correct but ugly. Always combine like terms in the numerator. Don't expand the denominator unless you specifically need to. Third worked example, and this one shows up so often in physics, statistics, and engineering that it's worth committing to memory. Differentiate x times e to the x. Two factors. F equals x with derivative 1. G equals e to the x with derivative, e to the x. The exponential is the unique non-zero function that equals its own derivative, and that's actually the definition of the number e we'll work through in episode 8. For today, take it on faith. Product rule, f prime g plus f g prime. 1 times e to the x plus x times e to the x. Factor out the common e to the x and you're left with e to the x times the quantity 1 plus x. That's the derivative. Notice the derivative carries the same e to the x factor, a clue that the exponential will dominate the function's behavior far from 0. This particular derivative shows up everywhere, integration by parts in the integral playlist, the hydrogen atom ground state in quantum mechanics, the exponential distribution in probability, Planck's radiation law for blackbody emission. Memorize the result. 4 pitfalls in roughly the order they bite. Pitfall 1, the quotient rule sign. The numerator carries a minus, and the two terms cannot be swapped because of that minus. If you write high d low minus low d high, your derivative comes out with the wrong sign everywhere. Sanity check, differentiate 1 over x with the quotient rule. Answer should be minus 1 over x squared, agreeing with the power rule. If you get plus 1 over x squared, you flip the order, recite the rhyme. Pitfall 2, forgetting the product rule entirely and writing, say, the derivative of x squared sine x as 2x cosine x. That's the product of the derivatives, flatly forbidden by last episode's pitfall slide. The right answer always has two terms, one with a prime on each factor. Pitfall 3. The denominator of the quotient rule is the original bottom function squared, not the derivative squared. In our second example, the denominator was x minus 3 squared, not 1 squared. Confusing the two silently inflates your answer. Pitfall 4. Less catastrophic but still costly. The rule produces a correct but often ugly expression. Simplify. Combine like terms. Factor common factors. Your grader, your future self, and every later step in the problem will thank you. Why does this matter for the rest of calculus? 3 reasons. First, the universe of functions stops being just polynomials the moment you leave the first 3 chapters of any calculus book. The functions that show up in physics and engineering are products and quotients of polynomials, sines, cosines, exponentials, and logarithms. Without these 2 rules, you'd be stuck running the limit definition every time. Second, we finally get to close a loose end from last episode. The power rule was proved only for positive integer exponents. The quotient rule, applied to 1 over x to the n, immediately extends the rule to negative integer exponents. The derivative of x to the minus n is minus n times x to the minus n minus 1, which is the same pattern. Bring the exponent down, subtract 1. The negative integer case is now done. Third, when we add the chain rule in the next episode, the 3 rules. product, quotient, chain, will combine to let you differentiate essentially anything you can write down by multiplying, dividing, and composing elementary functions. You'll never need the limit definition again unless you're proving a new rule. Where we landed, 2 new rules. Product rule, derivative of fg equals f prime g plus fg prime, proved from the limit definition using the add and subtract trick. Add and subtract f at x plus h times g at x, and the 4-term numerator splits into 2 familiar difference quotients. Rectangle areas picture, when both sides of a rectangle grow, the area gains 2 strips and a vanishing corner square. The 2 strips are the product rule. Quotient rule, derivative of f over g equals f prime g minus fg prime over g squared, derived in 3 lines from the product rule by writing f as f over g times g. Mnemonic, low d high minus high d low over the square of what's below. History, Leibniz published both rules in October 1684 in Nova Methodus, the first published paper in the history of calculus. Newton had equivalent results a decade earlier but didn't publish them. 3 worked examples. X squared sine x gives 2x sine x plus x squared cosine x. X squared plus 1 over x minus 3 gives x squared minus 6x minus 1 over x minus 3 squared, and x e to the x gives e to the x times 1 plus x. 4 pitfalls centered on the quotient, rule sign in order, the bottom squared, and the algebra cleanup. Next time, the chain rule, the third and biggest derivative rule for compositions. See you there. The product rule splits one derivative into 2 pieces and adds them. The way this channel splits into something larger is one comment, 1 share at a time. Thanks for adding your piece to the total. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.